In this unit, we are going to see the model fit and model selection, how well our Bayesian model is set, how well the data are corresponding to the model, and in the presence of several models, which one is the best. So first, we are going to talk about model fit, deviance criteria, and deviance information criterion, DIC. The deviance, we already talked a little bit about deviance before. We essentially said that if you have two models looking at the deviances, the model with smaller deviance is better in the sense that better fits the data. Although sometimes you cannot test deviance for itself, saying that this deviance is significant or not significant, definitely you can calibrate one deviance against the other and compare two models looking at the deviance. There are two ways how people set the deviance. There is just a definition that says take the likelihood, take the log likelihood, and -2 log likelihood is the deviance. The alternative, so-called saturated version of deviance, is calibrating this -2 log likelihood against the -2 log likelihood of so-called saturated model, optimal model, the model in which the data are modeled exactly. We already saw in dealing with generalized linear models how the deviances look like for binomial distribution, Poisson distribution, and the deviance for saturated deviance for normal distribution is essentially sum of these squares. Let's take a look how the deviance criteria works in fitting this data with two candidate models. For this data set, I propose two models to fit this with Weibull and to fit this with exponential, and to see which one is better. I will take non-informative priors on all parameters in these two models. And I will have two small ODC files, deviances ODC and deviances 2 ODC, and see what deviance is smaller and which model performs better. Whenever I have, for example, discussion of the ODC files, all these ODC files would be available on the repository, and you can try for yourself running all these files. Let's take this data set and let's fit this with Weibull distribution. TIs are Weibull. There are two parameters, gamma and mu. For Weibull distribution, I know the density. If I take log density and I take -2 sum of the log density or log likelihood, this is deviance. Let's call it dev. And then I put non-informative priors on mu and gamma and run this model. I get that this model, well, I monitor only deviance, dev, and if I put deviance, which is built in, I should get the same value for the deviance. So this deviance is built in, always there. You can always ask for deviance, which is built in. So let's see what happens if I have exponential model. Here I have a model in which times are exponential. For that one, I have also the density, which is the likelihood as a function of parameter lambda. Log likelihood is here, and the deviance is -2 summation log likelihoods. The prior non-informative here would be gamma with some small parameters. I run this, and I get that deviance is 46. I also estimated lambda here. For Weibull model, recall this was 43. This one is even bigger run, 2 million runs, and I see that the deviance of the Weibull model is smaller than exponential. Therefore, Weibull model is better fit. So that would be simply comparisons of deviances for the candidate models.